In the previous lesson, you learned how to factor general cases of quadratic trinomials. In this lesson, we're going to learn a little bit more specific cases, maybe special cases of perfect squares and also um, difference of squares. So we're going to look at those two situations today. But before we do that, I need you to memorize and recognize at least the first few perfect squares. And so if we take a look at this, we see 1 squared is going to be 1. If we look at 2 squared, it would be 4. 3 squared would be 9. 4 squared would be 16. Okay, you can see the pattern. So we got 5 squared is 25, and 36 is 6 squared, 49 is 7 squared, 64, and so on. Okay, so a good idea would be to get to where you could recognize these numbers. Okay, because when you're working problems involving factoring, it's going to come in handy to be able to know the perfect squares. Obviously there are more, but these are just the most commonly used for math class. So we're going to move on. We need to remember back when we did a lesson on multiplying special cases, not the factoring, but the multiplying. We learned that we have a specific case of a plus b squared is equal to, if you want to split it up, a plus b times a plus b, and then that is going to be equal to a squared plus 2ab plus b squared. Now obviously we could do the full method, but essentially if we did that enough times we would see this pattern. But we learned specifically this formula to be able to solve this situation. Also, if we have a minus sign here, then it's basically the same thing, except this 2 is now going to be negative. And once again, if you work the full method enough times, you would see that pattern as well. But now we're going to take that idea and we're going to think backwards. Obviously, this was learning how to multiply it, but in factoring, we're trying to take a trinomial like this, and we're trying to break it down into factors. And obviously, the end result would be the simplest form of that. So we're going to take a look at that, and I want you to write this down in the red. Now in the green, a little bonus for those of you who are paying attention, in this lesson I do not expect you to write down the green parts, but I do want you to write down this red. So as we move down, we're going to look at the rule for perfect square trinomials, and it's exactly backwards of what we just talked about, where if we have a squared plus 2ab plus b squared, we can take those numbers, take the square root of a squared, which is a, and the square root of b squared, which is b, and we can split this up. We have a positive sign here, so we know we have plus and plus, okay, which ends up being a plus b squared. And the same idea here, except for we have a negative here, so that means we take a minus b times a minus b. Okay. Now obviously every problem is not going to have a 2 in it and split up into factors in the middle, so we have to look for those forms. We have to make sure that it's in that form. So in this example, let's take careful attention to whether or not it's in that form. Okay, so let's look at this. We have m squared minus 6m plus 9. Now I know that I could bust m squared up into factors, and I could bust 9 up into factors of 3 times 3. So obviously those two are perfect squares because we've got m squared and we've got 9, which is one of my perfect squares that were up on that list. Okay, now the thing to check is we need to make sure that this is in the form of negative 2 times a times b. So let's take a look at this. We take an a, take a b. Okay, we say 2 times m times 3. Okay, so I've got my negative 2, and the only reason I use negative is because I see that it's already negative. Okay, so I take negative 2 times a, which is m, and b, which is 3. Okay, multiply this out, I get negative 6m. So it worked because it's the same thing there. So we do have a perfect square trinomial. Okay, so because we know that, we can simply use our rule that we just saw, okay, right there, and we use m minus 3 times m minus 3, okay? So we've gone from this step now to this step, okay? because we took a and a b, put it there. We realized this was a negative, so that needs to be negative, okay? And we could go ahead and combine those and say m minus 3 squared, and we would be done. Okay, so, and obviously you could check your work. The way to check any factoring problem is whenever you get your answer, use the full method right here and multiply it back out. Make sure that you get what you started with. That would be the best way to check that. Okay, let's take another look at another problem. This time, our first part, our A, does not just have a 1 next to it. This time we've got a 4, so we need to think, is that a perfect square? Because this can't work unless it is. 4 is a perfect square. So let's take a look at what the square root of 4n squared is. That would be 2n. So 2n times 2n would give me 4n squared. Okay. And over here we've got 16. That is a perfect square because it's on our list, and so we got 4 times 4. All right. So we've busted it up, and now I want to take this and check. We're trying to check this right here. Make sure that this actually is a perfect square trinomial. All right. So we need to say 2, positive 2 because that's positive there, times 2n times 4. Okay. And 2 times 2 is 4 times 2 is 16, and we only have one n in there, so yes, it does work. So it is a perfect square trinomial. So that means I can just take my 2n and my 4, and I can write this out. Okay, and because that is a positive sign there, I can put a plus sign here and here, which is just like last time equal to 2n plus 4 squared. Okay. And once again, you could fold that to check that answer every time. If you're ever unsure about your answer, go ahead and fold it and see if you can get back to it. All right, just like last time it's green, you don't have to write it, but let's remember from special cases, the next thing we're looking at the difference of squares. Earlier we learned that if we see this situation where we have a and a b, and they're written the same way, except for the only difference is a positive and a negative, then a shortcut would have been to write a squared minus b squared, because when you do the full method, the outside and inside would end up canceling each other off. Okay, so but we're going to take that, we're going to think backwards. If we see the difference of two squares, okay, we have a square, there's a difference, okay, then we can open it up and write it this way. Okay, we can factor it out in this way, just taking that same rule and just applying it backwards. So very quickly we're going to look at these because they are very quick. So we're going to make sure that we have two squares. Okay, a squared obviously is a square because you got a times a. 16 obviously is a square because it's on our list that we saw a few minutes ago. So 4 times 4. All right, and so we have the difference of squares. So we simply write a plus 4 times a minus 4. Okay, and like I said, if you want to check that, you just use the full method and you should get your original answer or original problem. Okay. Now, on this one, it looks a little trickier, but it's really not. It's just bigger numbers. Sometimes you may have to check, you may have to use a calculator or whatever you need to use. But if you get really accustomed to that list of perfect squares, you would realize that if you went all the way out to 15, then you have a perfect square here as well. So let's take a look at this. What number or what term could we use to multiply times itself to get 9b squared? If we think about this, we've got 9. The square root of that is 3. Square root of b squared is b. So if I did 3b times 3b, I would get 9b squared. Okay, and like I just mentioned, if we use 15 times 15, we get 225. And like I said, you may need to use a calculator or try out a few numbers and see what you get. Okay, but then we use the same process. Okay, we have an a and a b, and so we say 3b plus 15 times 3b minus 15. And we're done with that because it's very, very straightforward difference of squares. Okay, one more example and we'll be done. In this situation, if we look at this problem, we're thinking, okay, 5 is not a perfect square. 80 is not a perfect square. So we're thinking we can't go anywhere with this. But the thing is, if we see a common factor between these two. Obviously, if we're factoring, then common factors can be used, so we can pull those out, okay? So I see a common factor of a 5 in both of these terms, okay? So I'm going to take out a 5. I'm going to divide both terms by 5. So I'm going to stick this out to the side, okay? So 5c squared divided by 5 would be just c squared, because those 5's would cancel off. So I got c squared, okay? Bring my minus sign down, all right? And then 80 divided by 5 would reduce to be 16, okay? You could just do the division with that, or you could count it however you need to do that, okay? So we got 16 now. All right, now, within the parentheses, I believe we have different squares. We have a square here. Obviously, 16 is in our list of perfect squares, so we could just simply bust this up, and we could say c plus 4 times c minus 4, okay? But the thing you need to make sure is that you do not forget this 5, okay? Because without that 5, it would just be this part, okay? You need that 5 to get you back to that part. So if you want to check your answer here, you do the full method between these two, and then once you get all that, you would distribute this 5 back out, and you would end up with 5c squared minus 80. Okay, so I hope you can take these examples and these rules and apply them, and good luck factoring.